Good day. My name is Delai Sedro. I'm a PhD student at AUT. The title of my paper is The Effect of Parapets on Roof-Mounted Solar Collectors, and my supervisors are Professor Timothy Anderson and Roy Nates. So over the years, you would notice that the world has had a transition from the conventional sources of energy to renewable energy. But amongst these sources of energy, solar energy is shown to be the most promising, particularly because of it being non-polluting and exhaustible, and particularly because it's also very reliable. And so when the sun shines, you have two sources of energy at play. You have solar thermal that would usually trap the thermal energy, which normally would use for space heating or for hot water. And you have solar PV, which would normally trap the photons, which you normally use for electricity or for power. And so there's extensive literature that's shown interest in improving the energy yield for both photovoltaic and solar thermal. And we've looked at the prospect of architectural integration, probably new color and material, a tube arrangement in terms of the solar collectors, innovative fluid, radiant cooling, all in line with improving the performance of these technologies. Now, the way of determining the energy yield of a solar thermal collector is from the equation I've shown below. But of particular interest is the U value here, which denotes the heat loss from solar thermal collectors. So I explain this with a figure below. If you take an unglazed collector, such as this, a collector that has no covering whatsoever, no insulation, a typical flat plate, then you expect that as you absorb the thermal energy, if they have wind velocity being high, then you would expect that you would lose all that heat due to wind-induced convective heat transfer. In a scenario where you bring in a glazing, then of course that would limit the wind-induced heat loss on the surface, and so this will have a better performance in this case. And then if you have a double glazing, as you can see here, then of course you would have a far better performance compared to the unglazed collector. And so if you look at it, so in terms of cost, you would notice that the double glazing will normally be more expensive than the unglazed collector. So let's explain this in terms of photovoltaic as well. Now, when the sun is shining, you're having photons coming in, and so you're interested in the light and not the thermal energy. And so if the thermal energy is coming in, you want to have enough wind velocity to sort of reduce that or to have that wind-induced heat loss, so that the performance of the PV panel is better. And in the case of the solar thermal, it's opposite. You want to trap the thermal energy, and you want to limit the effect of wind on the surface of the panel, because if the wind is higher, then of course you're going to lose more thermal energy. And so we've explained that wind-induced heat loss are detrimental to the performance of solar collectors, whilst the opposite is the case of photovoltaic panels. And so the argument is that, look, we're looking at energy yield. We want to improve the energy yield in all cases, but we've also come to understand that climatic conditions can significantly affect energy yield. And then we also understand that wind velocity or wind speed is one of the factors that can really have an effect on the energy yield and on performance, as we've just shown. And so if you tie all of this together, you are looking at what is cost, performance, and heat transfer. And so these three things are married, and it's not something you can separate from the other. But we sort of look at, okay, a more passive strategy. And a more passive strategy is that if we have these farms that typically have windbreaks, as the wind blows, these windbreaks would normally minimize the effect of wind on the farm. And so it can minimize wind erosion, livestock, reduction of fugitive dust, agricultural wind drifts. And this is something that has been done over the years extensively. But these features already exist. These are already part of what we see every day. And these are in the form of parapets that we see on buildings. Architects use this extensively. And the fact that we mount these PV panels or solar collectors on roof surfaces, and the fact that we have parapets, it should be interesting to see how these parapets can mitigate the effect of wind in terms of the performance of the solar PV panels or solar thermal collectors. And like I said, parapets are common architectural features. If you look across literature, extant studies has been mainly focused on the structural support system of these PV panels. And the collectors, as opposed to how that relates to performance. But you can see from this image that these would normally mitigate the effect of wind on a building. And so we understand that side of it. And so in our work, we sought to look at the relationship between parapets and the heat transfer or heat loss from collectors, and probably vice versa in terms of PV panels. And so our study was a simulation study. We first of all looked at a 3D computational fluid dynamics using ANSYS solver, and then we did an experimental validation of the method. And then, of course, we looked at a comparative analysis and assessment of the two. One of the things that we did was to look at the building geometry and the parapet height. And so we looked at other studies like the Tokyo Polytechnic University and considered a building aspect ratio if the height is 4 meters, and then of course the width of the building will be about 16 meters, giving us an aspect ratio of 1:4. And then we also found out that in extant literature, parapets are classified as low parapets and high parametric parapets, where h is the height of the building and small h is the height of the parapet. Then we also thought about the wind incidence. So if we take this as a square, then of course we'll have wind coming in at 0. And so we looked at that all the way up to 180. And of course, since it's symmetry, you'll be seeing the same effect on this side. And then we also looked at the wind velocity. From 0.5 to about 10, and studies has shown why that wind velocity is often considered. But we also wanted to understand the effect of natural convection and forced convection, and so we considered that to determine what the effects would be. Another thing we also did was to look at the collector location, and so if you mount the collector 25% off the roof, a distance from the parapet, and then we look at it 50% and 75%. And so if you have a width of 16, that will represent 4 meters, 8 meters, and 12 meters. And then we consider the collector inclination angle. And so you will understand that the collector inclination angle is 5, 20, 40, and 60, as I've shown here. Now, for our experimental work, we undertook our experimental work at the University of Auckland Wind Engineering Group through the help of Professor Richard Flay and Dr. Lin Fa. And so you can see that we have a flat plate collector here, and we mounted several pressure points to measure the pressure on the surface of the collector. And then we had a free stream velocity and then also our atmospheric boundary layer. And so this was scaled to a scale of 1:20. And for our CFD, we looked at the K epsilon realizable turbulence model for the closure of our transportation equation. And we looked at the delta T of 60 with the plate being 330 and then the wind velocity being 303. So if you look at the first flow visualization, what you typically see here is that you notice that there's a recirculation bubble being created here. And of course, you see the same recirculation bubble being created there, which typically shows you that our experiment agrees with our CFD. And then we compare the pressure points, which I showed you earlier. And so we looked at that in terms of on the surface of one of the parapets. We compared the experimental data with the CFD data. And then we did the same thing as well for the surface of the collector. So we just chose one point or a path on the surface of the collector to compare that. And so when you look at our results, if you place the collector at the initial location of 0.2 in this case, what you would see is that over here, you see that the wind velocity is high. Although there's a recirculation bubble here, the wind velocity is higher in this instance compared to the lower parapet, and then it's even lower when the parapet is higher. And so it basically shows that the parapet is mainly minimizing wind, the wind velocity impact on the surface of the collector. And then you also get to understand that we said the wind velocity has an impact on the heat loss of the collector. But what happens when you move the collector a bit backwards? So if you move the collector backwards, what you get to see that the wind velocity is higher in this case, but then when you come to the lower parapet, you get to see that there's sort of a backflow from the leeward side, which of course can have an effect. And so the location of the collector is also very paramount in terms of how that affects the wind velocity on the wind flow patterns on the surface of the collector, which of course is tied into the heat loss from the collector. But what if we look at another interesting angle, 135, 45, 270? And so you'll see that when the collector is farthest away, you would have a significant heat loss because you would have higher velocity here on the surface of the collector. And that is a different case for when the collector is in front. And now we looked at the collector inclination as well. So an earlier study basically showed us that if we consider these two cases, you would typically see that when the collector is at a higher tilt of about 40 degrees, the wind velocity is higher, and lower when the collector is at 20 degrees, which is a lower tilt. Now, we sort of broke this down into looking at heat loss. And so convective heat transfer, breaking it down and normalizing it into a no-set number. And so if we take a surface such as this, and this is our parapet, and this is the cavity length, then of course we can convert this into an aspect ratio. And so if we take this to be the velocity of 2 and take this to be the velocity of 10, then if you just focus on this side alone, what you typically see that at higher parapets, even at higher parapets, the higher the wind velocity, which is about 10 meters per second, the more the heat loss, which is what you can see here. At no parapet condition, the higher the heat loss, or the higher the velocity, the higher the heat loss is, which is what you can see here, which agrees with extant literature and what we've basically seen. So in summary, we are saying that wind velocity near the surface of a roof-mounted solar collector can affect thermal performance. And of course, we know how that also plays with the PV panel. But then, of course, the higher the parapet, you're going to generate high suctions on the roof and the corners and some vortices here and there. And so we know that the parapet can have an effect on the performance of the collector. So overall, we've looked at the types of parapet. But what if we increase the number of collectors? What if we vary the collector angle of inclination? What if we vary the wind incidence, which are all things we've already done? And is there a way to tie all of this into a numerical model to say, look, if I have a parapet of this height and I have a collector at this angle, this is the likely performance you're likely to see? And so these are things that we have basically considered and we continue to explore as we've shown. But by and large, it's clear that the parapet can have an effect on the performance of solar thermal collectors and also on PV panels. Thank you.